Imagine a universe that is not quiet and empty, but alive with distant activity we are only beginning to glimpse. A cosmos where light does more than travel between stars, where it might carry patterns, structure, and perhaps even intention. For centuries, humanity has looked up and wondered whether we are alone, but only now, with instruments like the James Webb Space Telescope, are we beginning to test that question with real precision instead of imagination. One of the most intriguing targets in this search lies just a little over 4 light-years away, the Proxima Centauri system. Its planet, Proxima B, orbits within the habitable zone of a red dwarf star, a region where temperatures could allow liquid water to exist under the right atmospheric conditions. This alone makes it one of the most closely studied exoplanets in astronomy. But recent infrared observations have added a new layer of mystery. Subtle fluctuations in emitted light from the planet's dark hemisphere appear structured in a way that does not easily match known natural processes. What makes this especially compelling is not a single signal, but a pattern. Natural phenomena such as volcanic activity, atmospheric storms, or auroras tend to produce chaotic and irregular emissions. They rise and fall unpredictably, shaped by random environmental forces. Yet the light signatures associated with Proxima B appear unusually consistent over time, with repeating intervals and stable intensity changes. This has led researchers to cautiously explore whether these emissions could represent something more organized, though no definitive conclusion has been reached. Proxima Centauri itself adds complexity to the picture. As a red dwarf star, it is smaller and cooler than our Sun, but also far more volatile. Powerful stellar flares regularly erupt from its surface, capable of stripping away atmospheres from nearby planets. Despite this harsh environment, Proxima B remains within the region where life, at least in theory, could persist. If the planet has a strong magnetic field or a dense atmosphere, it might be shielded enough to allow stable conditions over long periods of time, creating a potential window for habitability. Scientists studying the planet have also focused on its atmospheric composition. When starlight passes through a planet's atmosphere, it carries fingerprints of the gases it encounters. In Proxima B's case, there are indications of unusual chemical ratios, including elevated methane levels that are not easily explained by standard geological models alone. On Earth, methane is closely associated with biological activity as well as industrial processes. Its presence in unusual combinations has therefore sparked interest, though it remains far from proof of life. The idea of artificial light naturally emerges from such discussions, but it must be treated carefully. What is being observed could have multiple explanations that do not involve technology. However, the possibility itself has become scientifically interesting because it expands the boundaries of what researchers are willing to test. If a planet shows repeating light variations, scientists must ask whether those variations come from natural cycles or something more structured. That question alone represents a major shift in how we study distant worlds. One hypothesis suggests that these signals could be related to large-scale surface activity rather than biological life. For example, reflective ice formations, shifting cloud layers, or atmospheric chemical reactions could produce changing infrared signatures that mimic patterns. Another possibility is that thermal emissions from the planet's surface are interacting in ways not yet fully understood, especially under the influence of a red dwarf star's intense radiation environment. Yet the most speculative interpretations focus on the idea of artificial illumination. If a civilization existed on a tidally locked planet like Proxima B, it would experience permanent day on one side and eternal night on the other. In such a scenario, artificial lighting could theoretically develop on the dark side, potentially visible as faint but structured emissions when observed from a distance. This concept remains hypothetical, but it has become part of scientific discussion because it offers a testable prediction: structured, repeatable light patterns that differ from natural variability. To explore these possibilities, astronomers rely on increasingly advanced tools. The James Webb Space Telescope plays a central role in this effort, using infrared sensors to detect heat signatures and atmospheric composition across vast interstellar distances. By analyzing how starlight filters through a planet's atmosphere, it can identify gases such as water vapor, carbon dioxide, and methane, all of which help build a profile of planetary conditions. These measurements do not reveal life directly, but they help narrow down where life could potentially exist. Future observatories are expected to refine this search even further. Planned missions such as large space-based telescopes equipped with star shades could block the overwhelming brightness of nearby stars, allowing direct imaging of Earth like exoplanets. Ground-based projects like next-generation extremely large telescopes will also enhance resolution, potentially revealing surface variations and atmospheric dynamics in unprecedented detail. Each technological step brings us closer to distinguishing between natural planetary behavior and possible signs of technological activity. Even with these advancements, caution remains essential. Astronomy has a long history of discovering unusual signals that later turned out to have natural explanations. Pulsars were once mistaken for artificial beacons. Strange radio bursts were initially considered candidates for extraterrestrial communication before astrophysical sources were identified. This context reminds scientists that extraordinary interpretations require extraordinary evidence, not just intriguing patterns. Still, the value of investigating such signals lies not in immediate conclusions but in expanding our understanding of what is possible. Whether the light from Proxima B ultimately turns out to be atmospheric chemistry, geological activity, or something entirely unexpected, the process of studying it forces science to refine its tools and assumptions. It pushes us to consider new models of planetary behavior and new ways of detecting faint signatures across interstellar distances. In a broader sense, discoveries like this reshape how humanity views its place in the universe. The search for life is not just about finding others. It is also about understanding how rare or common conditions like ours might be. Each new observation adds a piece to a much larger puzzle, one that spans billions of stars and potentially countless worlds. Even a single ambiguous signal can inspire decades of investigation, technological development, and philosophical reflection. Ultimately, what makes Proxima B so compelling is not certainty but possibility. It sits at the intersection of what we know and what we have yet to understand. The faint patterns of light, the unusual chemical ratios, and the harsh yet potentially habitable environment all combine into a scientific mystery that remains open-ended. Whether it leads to evidence of life or a deeper understanding of planetary physics, it represents a step forward in humanity's ongoing attempt to read the universe. As our instruments grow more powerful and our observations more precise, we may one day be able to answer these questions with confidence. Until then, Proxima B remains a reminder that the cosmos is still full of unknowns, and that even the nearest stars can hold surprises capable of reshaping our understanding of reality itself.